Hello everybody, I wish you're doing well. Today we will start a new special course because we will start by theory, then we will go into practice. So, what a bicycle, a mechanical watch, and a Tesla car have in common? They all rely on one unsung hero of engineering. Spur gears. These simple but brilliant wheels with teeth are invisible force behind almost every machine you use. Today, we're breaking them down. How they work, why they are everywhere, how you can design one in 5 minutes, even if you never touched engineering before. Stick around because by the end of this video, you'll see the world differently. Every time you hear click a wheel, you know that's gear at work. So we will start by the gear terminology. So we will see every part uh, of its teeth and every of its diameters. How do we call that? So here in the top, we have the top land. Here is the face, and in the in this part, we call it the flank. We will see how do we design these profiles in next videos. And this is the bottom land. The most important circle in gear, it is the pitch circle. So we have other terminologies that we will see in detail in this video, like the top diameter, reference diameter, base diameter, and we will see all the laws that allows us to calculate them. And if there is no law, we will define them and know them how we can use them. So let's directly start because I prepared some tables that will help us to understand all this. So here we have the parameter, its symbol, its unit, the description, and the formula or an example. So we have the module, this module, we have them in tables, and we have different series in these tables that are commonly used to design these gears, but some manufacturers use modules that are not so standardized to if we have a gear we can calculate directly this ratio or this module with using the ratio between the diameter and the number of teeth. And there is standard values, as I told you, as 1.5, and 2, and so on. We have the number of the teeth, it is said. We can count them, or we can use this law to calculate it. This is the thing that is important that I have shown you. It is the pitch diameter, the diameter with the teeth mesh without slipping. So it is here. It is the reference diameter or the pitch diameter. Then we have the circular pitch P. It is the balance between corresponding points on adjacent teeth. We calculated the P. It is pi times the module, and it is here. It is the distance between two teeth or two maximums. We can take it here to here. We can take it here until here. We can do it as we want. So the pressure angle is here, is the angle between each pitch. So it is here between this and this. So this is it. It is the angle between the line of action and the tangent to the pitch circle. For in general, it is 20 degrees, but it can be between 14 and a half and 25. We have other parameters as the base diameter. It is a circle which the involute tooth profile is generated. We can calculate by using this formula, and it is here the base diameter. It is under the reference diameter. We have also the outside diameter or the outer diameter of the teeth. We can calculate it by using that law. It is the reference diameter or the pitch diameter plus 2 times the module. So it is here the tip diameter or the outside diameter. It is, we can use the two names. We have the root diameter. It is d minus 2 times and half m for 20 degrees of the pitch angle. So we can find it here, the root diameter. And we have the tooth height. It is the height of the tooth. It is between this and this. We can find it here, the tooth depth here. And we have the addendum and the dedendum. We can calculate them with these laws, and they are here, the addendum, and here is the dedendum. So it's the height of the tooth above the pitch circle for addendum, and the depth between of the below between the pitch circle and the dedendum. According to this drawing, we can find the addendum here between this and this, because this is the reference diameter, and the dedendum here according to this reference diameter. So now we will talk about manufacturing and tolerance parameters. We have the face width. It is the width of the gear. We can find it here, face width. And the clearance, it is a radial gap between the tooth tip and the maintaining gear root. The thickness of the tooth at the pitch circle, we calculate it with this. And space width, it is the width between the width of space between two teeth and the pitch circle. We have as this theoretically. And profile shift x, it is the correction to avoid undercutting, especially for say Z under 17. So it is for gears that don't have much teeth. It is equal to 0 standard, but we can give it a value to improve the performances of the gear. So now we will see the meshing parameter. Center distance, it is the distance between two gears. The gear ratio, it is the ratio between number of the tooths or the velocities. The pitch line velocity, we calculate the linear velocity of this gear, and the contact ratio is the average number of tooth pairs in contact simultaneously. It is 1.2 for smooth meshing. So the material we in gears we will use different materials. In general, it is hardened steel with chemical treatment, and that is hardened. It is between 58 and 62 HRC, that is hardness, Rockwell hardness. We have also the allowable tangential load. It is the load that can supported by the gear teeth. Surface roughness, it is roughness. It depends of the roughness that you need. So it is it is between 0.8 and 3.2. In reality, there is a lot of types of roughness. We analyze them as we do analysis of in electronic engineering. For it is like signal analysis. So this is it. We do the same thing as signal analysis. And for lubrication, we have multiple types of oil that we use to lubricate this type of mechanical components. So we have an example of oil here, and we will have wear reduction. So a clear summary: gear geometry is defined by the module which scales all dimensions of the gear. The pitch circle is fundamental reference for all gears, calculation, and machine condition. The involute profile that we will see in the next video is generated from the base circle. You will understand this in the next video and how we do it. And in another video, we will see how we can apply this with CAD softwares, especially with CATIA and SolidWorks. And this will help us to ensure smooth constant velocity transmission. And I have an engineering tip before we end this video. I have an engineering tip for you. Always we design gear starting from the module and the pressure angle. It depends, but in general it is 20 degrees to ensure capability with standard tooling. You must, if you are in the industry, you will change pressure and angle. Of course, it depends of the company you work in, and you must check the contact ratio early in the design to avoid noisy or unstable meshing. If the T number is low, we have this example, apply a positive shift to prevent undercutting. Prioritize heat-treated steel and proper lubrication for high load or high speed applications, and try every time to use the good lubrication. It will increase the life of your machine and your gears. So thank you for watching, and don't forget to subscribe, like this video, and ask any question in the comment section. Choose.